Okay, have another lecture on GE. Before I get started, though, I'll have a review session on Thursday during class, and again, labs canceled. And then can provide more details about the midterm. I guess before I get started, any questions so far? Okay. I'm going to talk about just sort of GE in practice at the beginning, so we'll just do some examples. Kind of the best way to learn it is really just to show how it can vary across different data situations and what's important, and in terms of how you make decisions about what things to choose, like working correlation, et cetera. And at the end, I'll give you a little, it's like I don't expect you guys to be able to mimic it, but just a heuristic proof for how exchangeable versus independent actually reweights the data. You can see, based on an example, about what essentially happens when you have a combination of unbalanced data, high correlation, and independence versus exchangeable, what kind of answers you get, and how you can explain how exchangeable might differ from independence. It's not perfect and it's not universal, but it gives enough insight, I think, for what we care about. Okay, we're gonna use start with the binary outcome data. So we treated this in different ways. Oh, sorry. That's good. Thank you so much.
Also, I think a lot of people were wondering about like the use of AI in the exam. If you want to just.
Yeah, I was going to say no AI during the exams. Okay. You can bring your computer and use it.
Yeah.
But. So anyway, the data we're going to look at is this repeated measures. We've looked at it different ways, right? But today we're going to look at it as just repeated measures data. And we have a binary predictor and a binary outcome. So it's very simple. If we were just given cross-sectional data like this, we might do like 2-by-2 table, get an odds ratio, relative risk, and call it a day. Because of that residual correlation of observations made on the same subjects, and in this case it's relatively high, we have to account for that correlation. So we're going to do like a logistic regression, except we're going to use GE to account for that correlation, both in the estimation by choosing a working correlation, and in the inference by accounting for it when we get our standard errors. So again, this is our basic structure. We have an ID. It's done by the day. We have a binary predictor. It's yes for 1 for yes if drug and alcohol use was reported, and 0 for no. And outcome sexual activity, 1 for yes and 0 for no. And again, there's a wide variation of how many days the actual participants in this study called in. Some called in almost every day, some called in one time. So it's against that situation where the data is highly imbalanced. This is not so important for what we're doing today, but just to show that if you have a date in it, and this data set has a date, it doesn't automatically, when you read the data in, assume it's a date. You have to convert it to a date using the date commands. So then, as you probably maybe know, it stores it in some format, which is like a Julian date. So it's like the number of days since, I think it's January 1, 1960 or something like that. So it stores as integer. And it also has this class that's date, so it can go back and forth between displaying as a date, or you can take differences of date and it'll give you back the days and that kind of things. But you always have to do this when you have dates. And so this just shows you how I did it. I was getting the min date here, so I want to get by person what is their minimum date that they're starting. This is just a simple look at the drug and alcohol, so 0 and 1 versus the proportion of all days that are reported in that group that report sexual activity. So just to get some idea about the descriptive nature of the data. So it's 25% if they reported no alcohol and drugs that day. And again, this is averaged over people and days. And 1 is 0.37. So you see an increase in reported sexual activity if you have drug and alcohol who's reported on the same day versus not. And then, of course, some of them are missing for drug and alcohol use, but they reported sexual activity. That's a pretty small number. Just looking at the distribution by so the count is by subject here, where I'm looking at both the distribution of the proportion of days they report sexual activity, and you can see it's a lot here at the lower end. So some report 0 of all the days recorded among this group of teenagers, and there's some all at the end that report more regular sexual activity. Some of these are based on very small numbers, so some people that recorded high probability of having proportionate days they reported sexual activity also don't have that many observations. That will actually affect our results in the end. And this is just the same with drug and alcohol use. Again, kind of a similar pattern. A lot of people reported no use of drug alcohol use during the course of the study, and you have that same table. So you have a real kind of skewed distribution to the right of these two variables. And this also has an impact because these people are also tend to report less days than the people on this side. So both had roughly 25%. That's not quite true, but anyway, that's just a summary that I went over. So we'll fit a simple model here. It's a logistic, that's wrong, logistic. But we'll use GE. So again, it's like logistic regression, and you sort of interpret the parameters the same way. You get those those coefficients on the covariates, which are like odds ratios when you exponentiate them. So we'll look at that. We'll get the estimates and the resulting inference for two different working correlations. Again, we don't have a huge choice here because with very irregular data, so you can always do independence. You can always do exchangeable. Some of the other more complicated ones like unstructured are unavailable here. So you just can't use them because the data is too imbalanced. And that's often the case. When you have imbalanced data, practically you have two choices, typically. You might be able to fit the one that's based on spatial or distance in time, but as I said, that's for some reason buggy and hard to fit. Can't do autoregressive, can't do unstructured, which requires balanced data, or very close to balanced. Again, just to remind you, when we do independence working, that's just like we're doing logistic regression, treating all the data as independent when we get our estimates. Again, that's the first step. Second step is get the inference that now estimates the correlation of observations on the same subject without a model, just as a non-parametrically I went over last time. So I should get the same estimates here, same as simple logistic. And again, we'll see, we'll get a naive estimate of the standard error back that always reports that again, we never report that one. It can be interesting to compare it to get some insights about the estimation and inference. And that's always based on assuming the working correlation model is true. In this case, that'll be true. If I assume independence as a working correlation, it's going to assume all observations are independent, right? When it gets its naive standard error. So naive. Even on the same subject. Again, we don't report that. We're going to get we'll report the robust standard error, which allows arbitrary correlation. That will be a less biased estimate of the standard error. And again, just to remind you, standard error is estimated standard deviation of our parameter estimates in repeated studies as the one we did. So if we repeated this study, collecting the same number of subjects from the target population, did over and over again, we're trying to estimate that sampling distribution. If we get our coefficient estimate every time and draw a histogram of it, it'll be normal with some standard deviation, and that's what we're trying to estimate by the standard error. So we can get inference, p-values confidence intervals, etc. So here we've seen this in lab already. So we're doing GE. There's a couple of, I'm going to use GE in here, the GE library. There's also library GE Pack. There's different ones you can use. They shouldn't give drastically or different answers at all. There's little bells and whistles that may differ. GE is kind of the simplest one, so it's the one I teach here. Again, it's very simple. We have the Y versus the X, in our case, both binary. Family binomial, and correlation structure independence. Generally, you would put, I didn't put it here, we put NA action equals NA dot omit. Omit. If you have some missing values of either the Y or the X, you might put that there, because otherwise you have to tell it what to do. I think this data was structured so those were removed, but that's not always the case. So we got our estimates. Here's my beta 0 hat and my beta 1 hat. Again, the model is the probability. Why is it doing that? That's our model. And again, just to remind you, this is the same as saying the mean. Give an Xij. They're equivalent. Always go back to remember, we're just doing modeling the mean. Turns out the mean of a binary thing is also a probability. I just do some things here to give an output that looks okay. These things aren't necessarily written for producing the best output. You can use this code or not, depending on how you want to display it. But this just gives me the p-value, which doesn't come with the package, which is, again, the p-value is based on this test statistic here. And of course, I can just look up at a standard normal to get the p-value from those test statistics. So here's our estimate. We get a naive standard error of 0.12 and a robust of 0.18. What does that assume about how good a model the working correlation is here of independence? Are those numbers similar or not? Just in terms of percentages. They're pretty different, right? So that would imply that when I relax the assumption of independence, when I get my standard error, allow for correlation, the standard error changes a lot, which means independence is probably not a great assumption in this case. And that makes sense. There are kids with we saw that from that graph showing the distribution and proportion of days reporting sexual activity, that there is appeared to be a wide distribution there, so that would imply correlation. If you could be a person that tends to have higher probability of zeros, and a person that has higher probability of ones. So that all makes sense. Again, if I reported the inference, I'd be based on this one here. But this gives you some insight that my working correlation model is not great, because those are so different. And if they're very similar, would imply, doesn't guarantee it, but implies that the working correlation is a pretty good fit. I wrote that. I don't expect you to go through this at all, but I just, in case for transparency, it's also in the R Markdown file. This is my version of LinCom, which we talked about on how to get like post hoc estimates of associations that we specify as linear combinations of coefficients. So it's just doing that for GE, which didn't have maybe there exists a package now that will do this, but it didn't exist before. So I just wrote this so you can use it like LinCom. It's a slightly different syntax, but it's pretty close. So now I just feed the results in. I get the comparisons I want, which you can't see. Do I have the comparison up here? Yeah, I want 0 versus 1. That's what I want for comparing the x is 1 versus the x of 0. So then I also have to report exponentiate equals true, because if it'll return, if I don't, a log odds ratio, and I want to exponentiate that to give me the odds ratio. And I get an odds ratio about 1.74, okay? So with this confidence interval and this p-value. So you say statistically significant association based on the robust standard error of alcohol and drug consumption and reporting sexual activity in the same day. It's not exactly a rare outcome in this data set, so you can't really treat this as a relative risk. Relative risk is going to be something lower than 1.7, but say roughly a 50% increase in reported sexual activity if you have drugs versus not. Okay, any questions about that so far? So that's one working correlation model. Then we'll do another, same exact analysis, but now we'll replace the independence with exchangeable and see what we get. So all we're changing here is this, right? Just the exchangeable as the working correlation. That allows, during the estimation part, it reweights the data based on this estimated equation I provided earlier. It weights by the inverse of the variance covariance matrix for a subject. Now that allows for equal correlation. So it has to, one, estimate what the correlation is. Assuming that model, it has to build that variance covariance matrix for each of the individuals. And then you would get something like weighted regression, where it's a function of that, both the estimated of the correlation at this point is working. We're not estimating the true one. We just have a working one to try to capture some of that correlation in how we re-rate the data. And we see here, we got our estimates. Here's our naive for the one we care about, the beta 1 hat, and the robust. You can see they're a lot closer, which would imply, well, 0.12 to 0.14, not exactly the same. Again, you'd always report the robust anyway. That implies this is probably a better model because the standard errors are similar now. So that's something to remember perhaps for the midterm, right? If I give you output and I say, what does this imply about the working correlation? Is it good? Is it bad? You're just comparing the robust to the naive standard error. Again, this standard error is assuming, this assumes equal correlation of observations within subjects. Can we always assume there's no correlation between subjects? It's such that the default. It knows which those observations I by giving it the ID command. That's how it figures it out. And so it's not. It doesn't assume independence. It assumes something, a bigger model now. So the bigger model you assume, the more likely it's going to get closer to the truth. At least as you go, the sample size grows. And in this case, it's relatively close. And we get a much different odds ratio, right? Again, the standard assumption, if you ask ChatGPT, how does the working correlation affect the estimation in GE, it would tell you, it just changes the efficiency. If I get a better one, I get a more efficient estimate. The robust standard error will get smaller. But this is not, I don't even think the confidence intervals overlap. This is not the same estimate. It's not the same parameter because the data has been fundamentally reweighted. And we're going to try to understand that through this lecture. So this is a different estimate. It's a different parameter. It's a different projection. It's really just think of it as just weighting the data differently. And it's going to be weighting it as a function of how many observations per person. That weights differently in independence, where the more observation you have, the more weight you have. And the relative weight is just proportional number of observations. In the exchangeable, it doesn't work that way because things are highly correlated. If you have high correlation, so it estimates that if the row is relatively big, so high correlation, it will downweight those with lots of observations and upweight those with fewer observations. So it gets closer to not perfectly, but closer to every person weighting the same and not every observation weighting the same. So I think that's a good sort of rule of thumb. So independence. And again, this isn't exactly true because it's more complicated than that. We have covariates and other stuff, but it's close enough for this. Ways. So exchangeable downweights observations for subjects with high numbers of repeated observations. In the independence case, more observations means more weight, and the relative weight will be proportional.
Does it print the initial bits with the independent structure first, and then that's when it prints? Because the first part is the same, the first coefficient.
Oh yeah, that's funny. These are just the initial estimates.
So those are the initial estimates,
Yeah.
and it updates it using the exchange.
So you can ignore these.
Okay, got it.
Absolutely. These just ignorable. Sorry about that. These ignorable. So it seeds the estimation procedure by doing a regression without any assuming independence, because that's the only one it can do, because you need the residuals, you need a regression to estimate the correlation. So you can always ignore those initial. Those will be the same in the case of independence, but exchangeable it won't be, because it starts with independence and then it iterates by estimating the correlation after it gets one regression done, and then reweighting the data and regressing it, then re-estimating the correlation, and does that until nothing changes anymore. Yeah.
So in what situations would you rather, because it seems like the independence one is better because like it weighs like the different correlations, right? But the exchangeable, you're making it all equal. And so like in what situations would you use one over the other?
I mean, it's a very good question. It's not an easy answer.
Okay.
My general advice is if they're very different, use exchangeable, because what it implies is that there's a bias there from where you have the relationship between the number of observations and the association of the exposure and the outcome.
Okay.
And therefore, I mean, it could be situations where you simply want to get an estimate where you don't want to consider the distribution of observations per subject. Like if I'm doing prediction, for instance, and I'm gonna get a random observation in, and I don't care if it's 20 for one subject and 1 for another, maybe it's better to just do independence in that case. But when you're trying to make inference about the association, the differing numbers of observations per unit, in this case per person, is usually a nuisance. You don't want it to factor into your estimation. You'd rather it had a study that had controlled the number of observations per person. But again, that's not rigorous. It's
Yeah.
just, so, is that what you're asking?
Yeah, I guess in my mind, just like knowing, just like what I'm listening to, it just seems like the independence one will be better used because it does weigh every observation the same. Like given like different correlation between all the subjects compared to exchangeable where you're saying like they're equalizing, like they're making it all the correlation the same, right? Am I
Yeah, well,
getting
the
that
way the
wrong?
exchangeable works, we'll actually go over the technical details a little
Oh,
bit,
okay.
but the way exchangeable works is the number, if you have very low correlation, right,
Mhm.
they're not gonna be any different. The
Yeah.
independence exchangeable will get you the same estimates.
Yeah,
It's when correlation is very high. So what I like to think of the extreme situation that's almost one. It's the absurd one, but extreme situation. And that, there's no new information if you get another observation. So every person should weight the same. You shouldn't get more weight
okay.
if you had 40 versus 20, because you're not providing any new information, right?
Okay,
That's one way to think about it, I
okay.
think, heuristically. But again, this isn't like rigorous, it really depends on what you're trying to estimate. And if you use it for prediction, you would do some sort of cross-validation where your new data would come in the way it would come in practice. You would mimic that, and you would see which of these did better, because they're different estimates, right? So they're gonna give you different estimate accuracy for prediction. So I wouldn't say it's objective for prediction. Usually I think for more causal associations, your related association, exchangeable in this context will tend to be more defensible, but
Okay,
not perfectly.
okay, good to know. Thank you.
So the naive assumes equal correlation of observations within subjects, and it does that both in the independence and the exchangeable?
In the independence, it doesn't estimate correlation because it's using a working model to estimate the coefficients of independence, which is just like standard logistic regression. There's no reweighting based on the correlation of observations within a subject. So it estimates based on your working correlation. That's the estimate of coefficients you get. Then when you go to the standard error part, the robust standard error, it recalculates the correlation matrix, but assuming nothing. So it allows everybody to have their own different correlation structure. We saw that it could estimate correlations by just a residual on one observation times the residual of another observation. It gets very poor estimates of each correlation, but they're non-parametric, they're not making any assumptions. And it just turns out when you get your standard error, it's like an averaging across that big matrix. So the fact that each one is terrible is less important than when you average across all of them. It's stabilized, it's okay.
And it does the same within the independence and exchangeable
Yes,
approach?
it's the same. So exchangeable, then when it gets to the inference, it also doesn't assume anything when it gets to the standard error. So the standard error part is the same no matter what your working correlation. Of course, there are different estimates, so they won't give you the same standard errors or necessarily.
So basically the naive is the standard error of the correlation that you are assuming, the independence of the exchangeable, right? And the robust
This is the naive, this assumes, like you don't use it, right? You only report that one, but this
Uh-huh.
is a standard error in this case that assumes exchangeable is the right one.
Yeah,
And this assumes nothing.
exactly. Thank you.
All good questions.
So the robust under the independence and the exchangeable shouldn't be the same.
The what?
The robust standard error.
No, they won't be. They're different parameters. That's what I'm saying. They're different things. They're not the same thing they're estimating. They're different projections
Yeah.
of that model on whatever space. I mean, this is a non-parametric model. It's just a binary thing. So
Mhm.
it has a little less to do with that. We're going to do a continuous example. I think the best way to understand this is just you can, and we're going to go over it in some detail. We're going to talk about fixed effects models. Then we talk about mixed effects. So fixed effects, have you heard of like Mantel-Hansel odds ratios?
No.
Okay. So Mantel-Hansel is where you have stratified 2x2 tables. So for every person, I can make a 2x2 table of their X's and Y's, and I can estimate an odds ratio for every subject, right? And then I can average them across each of the odds ratios. That's essentially what exchangeable is closer to. And independence is closer to, I just make one odds ratio, one pooled table and get the odds ratio. So, and it turns out, because there's this classability thing with logistic regression, it's a weird mathematical fact that I don't think is that important. Those aren't necessarily the same things, even if it's not a confounder ID. But essentially, you treat ID like a confounder, and then I get an estimate of the odds ratio per subject, and I average them somewhat based on the relative sample size across the tables. And we'll do this explicitly, so you'll see it explicitly, but that it has more to do in this context with the binary outcome and just the binary predictor of the fact that the odds ratio has this property where it's not collapsible. That is, even if it's not a confounder, the pool table will be different than the stratified table, as long as the thing I'm stratifying is related to the outcome. Usually it has to be related to both the outcome and the exposure. So it's closer to that, but we'll do that explicitly. So that's a fixed effects model where we just basically treat our ID as a variable, essentially, and we adjust for it directly. And there's ways of doing that so you don't have to estimate a coefficient for every ID and things like that. So I just point out, if I keep the same, if the design's the same, so if I collect more and more data on subjects, but still have that same distribution of the number of days they report data in that data, and I let the number of subjects goes to infinity, I'm not going to get the same numbers for these two estimates. They're going to be different numbers. They're not going to converge to the same number. If it was balanced, they would be. But in this imbalance, if it continues to be imbalanced, asymptotically, they're not the same things. You can always tell by saying, okay, what happens if the sample size goes to infinity? They should go to the same number, if the same parameter. They won't go to the same number. So they're different things. It's hard to describe what they are exactly. They're two estimates of the odds ratio, in this case, that weight the data differently. And that's always the case it's going to be. So that's why it's not taught typically, because it's a very inconvenient fact. It doesn't lead you to sort of snappy interpretations of one versus the other. The binary case is a little different, which we'll get back to. Continuous case is more classic that we'll study now. So again, we'll revisit this when we talk about fixed effects models, random effects models, etc. For now, just think of them as just there are two ways of weighting the data. If, in fact, the data is balanced, we'll see. It doesn't matter what correlation structure you do, you get the same estimates. Having equal correlation doesn't re-weight the observations on the subject if everyone has the same number of observations. It only does it if people have very different numbers of observations. Basically, based on that heuristic I just gave, which is correlation goes to 1, you'd expect every person just to have a weight of 1, because there's no benefit of taking replicates on a person. They don't give you new information. So it does it automatically. You don't have to worry about it in a sense. You just let the procedure do it. And
So if it's unbalanced, it would be better to go with exchangeable.
it doesn't matter.
Unbalanced.
Oh, unbalanced is generally, that's the argument I was just making. It's generally better, depending on what you're doing, but to go with exchangeable, because that's usually what people want.
So when people say that you get consistent estimates for GDE, no matter what your working correlation structure is qualified by you have to have balanced data.
If you don't care what your working correlation is?
Yes.
Yes.
Yeah. Okay.
So if you have balanced data, same number of observations per subject, it won't matter.
Right.
I mean, you can get slightly different answers if you have autoaggressive versus let's say unstructured. Those can be slightly different, but they're not going to be they're going to be hugely different. If they're really different compared to the standard error, it means I would always go with the estimation using exchangeable for the reasons I said, but I think it's debatable. And again, at the end of this, we'll get into some explanation for just some simple math that sort of shows how it actually works in practice, how this weighting changes as I use, if I have high correlation versus not. So just to give you an understanding, we have like these are real data sets, but they're artificially created from our HIV CD4 count. So we have continuous outcomes, and then we have some binary predictors and then continuous predictors. So we'll do, for each of these comparisons, these data sets, which are available on the B courses, we'll just do kind of this. This is the same as G with independence. It's just like standard linear regression. Again, we're not doing logistic now. We're going to do just standard linear regression. And then we'll use G, where we look at both the naive and the robust under two different working correlations, exchangeable and independence. And then we'll summarize at the end. So if you get a little lost during all these models, don't worry about it. We'll come back to it. So what we're going to do for each of these, we'll compare the naive to the robust standard error. We'll compare the estimates if you used exchangeable versus independence, and we'll go from there. Again, so this is data. This is based on a situation where you have one predictor, it's binary, and it's time independent. And then we just have, in these first two cases, just have 2 observations per person, so they're balanced. So for every subject, they're either going to be a 1 or a 0, it's binary age, and then you have the outcome, which is a CD4 count. So again, the data will look like this. Just it's repeated measures, but everyone only has 2 observations, and they'll have the same predictor for both because it doesn't change with time. So first I'll do, it's just CD4. So again, this is the Y, this is the binary X. Y is continuous again. A family Gaussian, that's just linear. So no transform of the mean model. And then correlation independence, again, we can ignore this stuff, although it'll be identical to here. And we get our estimate. So here, we're going to focus on the intercept. We'll focus on the coefficient on age. It's estimated to be 24. The naive standard error, assuming independence, is 14, and the robust is 19. So it tells you that's probably not a great assumption of independence. They're probably correlated. They're CD4 outcomes, even conditional on the age. And we don't have a strong association based on that standard error. Okay, so that's one. And again, we'll summarize in the end. So you can compare these directly. But here, again, going back to that, we have our estimate. It's balanced data. We're not comparing it yet to exchangeable. We will, so we'll see what that implies about how the estimates change. The standard error naive underestimates the true standard error, the truer one, which is the robust. So it's underestimates. And the naive is just like if I could replace this with just, if I only cared about the naive, I could replace this with just LMM. It would just be equivalent to linear regression. No difference. The only thing it's given me here is I have the robust standard error I get, which is still trustworthy. Okay, only thing I'm doing here is changing exchangeable, same data. You'll notice when you look at the end, the estimates are identical now. Data's balanced, whether I assume equal correlation or no, it doesn't change the relative weighting of subjects anymore. They all have 2 measurements, so there's no reweighting, even though there's obviously some residual correlation because of the balanced nature of the data. You can see the naive here is almost equal to the robust standard error. And in fact, the robust standard error is also exactly the same as the robust I got from independence because it's the exact same estimator now. That should only change that the estimator is producing a different parameter estimate, but it's identical. So the robust will be the same for both this and independence. And again, this is closer because allowing for some correlation gets you closer to the true correlation structure. Even when I break the assumption that they all have to be equally correlated, that assumption appears to be pretty good in this case, close enough. Again, just to emphasize, you would only report that one, but it wouldn't matter in this case either. They're both the same. And therefore, my inverse is exactly the same. Same p-value, same confidence intervals, all that would be identical here. Okay, so here's a new data set. Also, same structure, almost. Binary predictor. Only 2 measurements per person. But in this case, everyone has I think it's viral load. We use median viral load. It has a low measurement and a high measurement. Low is 0, high is 1. So it's time dependent now, right? So these time dependent and balanced data. It's structured so everybody has the same pair of exposed versus unexposed. So it's almost like a crossover trial. You can think of it where I have a situation where you have a treatment and I get the outcome, the situation where I have control, I get the outcome. It's artificially created, but it has that structure. Okay, so it's balanced data. What do we expect in terms of the estimates? Will they change using exchangeable and non-exchangeable? No, they'll be the same. We know that. And then we'll look at the standard errors, how they change. So here's independence. And let's look at the naive. Naive is 30, and the true is 15. So now it overestimates. And this is kind of a typical phenomenon you see. So you kind of think, oh, if I'm ignoring correlation, I'm going to underestimate the standard error. That's not true in every circumstance. If you have time-dependent things, you actually can use that correlation to get better. You're essentially implicitly using that correlation, and you can get better estimates, lower standard errors, than if I only had one observation per person, or I ignored the fact that these observations coming from the same people. So I can tell you, I can give you a heuristic what it's like. So if I have like y, ij, and xij, and this is 0, and this is 1. Let's say I have data like this. If I just treated the data like this, so I didn't let the procedure know that there were repeated measures here. It's just like doing an analysis, treating every observation as independent subject, right? And so we get the mean here, and compared the mean here, and this would sort of be the variance, right? But once I know they're the same subject, I can connect the dots. Oops. So let me just dot, 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 dot. And now that I know the same subject, and I actually get a difference, right? For every subject I get there, 1 versus 0. And you can look at those, there's almost no variance in that. It gets rid of this variance. Once I include that in my standard error calculation, it can see this correlation happens like this. So in this case, you actually overestimate the variance by ignoring the correlation. And this is why crossover experiments are often are considered like powerful if you can do them, because you get the person serves his own control. You get rid of between person variability. This essentially I'm able to do here. I mean, I'm not doing that explicitly. It's just the correlation structure recognizes it and does it itself. So that's a circumstance where when you have time-independent things, sometimes the naive standard error, semi-independence will overestimate the standard error. When it's fixed covariates, time independent, it often underestimates the standard error of semi-independence. Again, practically you don't have to remember, just report the robust standard error, it'll do it for you. But that's what the phenomenon is happening here, the fact that it essentially it's including the between person variance, which the correlation realizes when you estimate that, it essentially subtracts that out, and you get an estimate that's standard is closer to the truth, which is the fact that it's more like a paired t-test, right? If we do exchangeable, again, naive and robust, almost identical. Estimates are exactly the same as we saw previously. There's no change from the initial fit, assuming independence here. So the same phenomenon. Right. Again, in this case, it wouldn't matter what correlation structure you assume between these two. Going to give you identical answers. Identical robust standard error, doesn't matter. So in balanced data, typically you might be if you have balanced data, you have, as I said earlier, the choice of your working correlation isn't going to matter very much. It only matters when it's complicated. When you have imbalanced data, then of course the interpretation of which is better has this kind of loosey-goosey way of it. I've explained it. It doesn't really have a rigorous preference, except for what I said about exchangeables. What I tend to argue is probably better. Okay, finally, we're just going to do unbalanced data. So this is just I'm going to have a baseline log viral load. So that's time independent. Then I'll have the log viral load change. So again, my model's like EYIJ given XIJ and XI1 is beta 0 plus beta 1 XI1 plus beta 2 XIJ minus XI1. Okay, why am I including this one? Remember that lecture? This is an important thing to remember for the midterm. Well, I have a history. I can adjust for it now, right? And so we talked about how confounding might come through unmeasured individual characteristics through the current exposure. And if I include that, I get rid of some, maybe the bias of how people enter the study and things like that. We did those plots that showed the cross-sectional. That's this one versus the longitudinal effect. So this one looks at the within-person change. In person, I should say association. And this one is the between person. And this is typically a nuisance. And this is the one of interest. You can go back to that lecture and see the explanation. So I'm just doing that here. It has nothing to do with GE or how I fit it, right? This is just a modeling choice that says I'm going to adjust for the history in some way. In this case, I adjust for the first viral load measurement, but I could adjust for, I could take out the first row for a subject and use their outcome as the adjustment variable, would have that same kind of property. So in this case, data is highly unbalanced, right? Some people come in for lots of appointments and get their viral load and CD4 measures. Others come in very few times. That's probably informative. People that come in more could be sicker because they have to go to the doctor more often. For instance, that's just one way that a bias could enter. And so it's important to have this adjustment of the history to see what is really the effect of a change in viral load on CD4 count and not maybe people come in differently and that would cause a biased effect of some kind. So anyway, I do this, assuming independence. Again, it's a linear model. I get, this is my beta 1 hat. And here's my beta 2 hat. Let's just look at this one. That's my one of interest. So naive standard error is 2.4, robust is 6.8. So obviously, assuming independence probably wildly underestimates because there's probably high correlation of observations on the same subject. So that's the first one. Let's just do it with exchangeable and look at how those things change. Here's our estimate. Here's now, everything's the same except for I'm now using exchangeable, and you can see it's about half the magnitude of the original one. The original was 100, had 100 decrease in the mean for a log 10 unit change in viral load. This one is half that, just 50. This is a little bit closer. Again, so exchangeable is better than independence in terms of the model of the correlation. Of course, you use that one anyway. And this just right here gives you the estimated correlation. So when you use a exchangeable, you can get back that estimate of the equal correlation. That's 63.63, very high correlation. So we would expect that assuming independence is going to exaggerate the amount of information somebody with lots of observations versus a small number contributing. And we really are reweighting the data in a way that's giving us fundamentally different estimates. Yeah.
And the way you would interpret this is that for each 54 reduction or negative change in the viral load, for each unit of reduction of the viral load,
Log viral load. So units a tenfold.
Yes, you will have 54 less CD4 count.
Yeah. So it's the direction you expect. The other thing to note is look at here. The cross-sectional is about the same as the longitudinal effect. So that would suggest I could have done a cross-sectional study and done a pretty good job. That tracking the within individual, the scheme of that from between the individual, in this case, the way I adjusted for it, which is putting in that, didn't really, gives you very similar.
Or also the time window for observing the outcome is not enough for seeing the impact of the change.
Explain that to me, I don't get
So,
that.
for example, if I have a change, if I measure the CD4 counting the same day of the change, like the second day, I will not see the effect of that change because the change in the CD4 count is gonna happen in 3 days or.
Yeah, well, this has no lag built in.
Yeah, no, I'm just.
Right, so that's another thing to consider. Maybe I don't want the instantaneous. I mean, this change I put in here, this one here, is changed from the first day.
To the second. And
No,
the
it's the first, it's
I'll
the
give
second
the
day to the
last
first,
one.
third day
Got
to
it,
the
got it.
first, fourth day to the first.
I got it.
Yeah.
And I have another question. For adjusting here for the history, can you also include the outcome
Yes.
at admission?
I mean, you can't use the first observation because that will, you have to use that outcome as a predictor then, right? So that's almost always a very good idea.
Mm.
If you're the instantaneous effect of something, what better adjustment variable could you get than the outcome the previous time, right? Here. So, yes, always a good idea. Yeah.
Sorry, can you repeat again why the exchangeable would cut down the estimate by that much? Would cut it in half compared to the
I'm gonna get to it right now.
Yeah, sorry.
No problem. That's a great question. I mean, again, I'm going to give explanations that are probably somewhat close to the truth, but the complicated math behind it, I can't give you a single answer, but this is probably the most likely explanation. So again, just remember, let's go to the summary results. So here's the summary. And this is useful for sort of looking at these two situations of balanced data and seeing how the naive is relative to the robust, and how the naive can underestimate or overestimate depending oftentimes on whether the variable of interest is time independent or time dependent. And for unbalanced data, as we've been talking about, they can just be radically different. So let's try to get a sense of what is exchangeable getting closer to that we can sort of mimic it in some way. That was my idea to go through this. So I know from what I'm going to show you later that what exchangeable does is sort of compress the relative amount of information subjects provide to the regression coefficients. So we start out with independence. If you have lots of observations, if you have 100 times more observations than that one person, you're going to provide 100. You're going to be 100 times more influential for the regression. So your data is going to matter a lot more for that estimate than somebody that has one observation or two observations, et cetera, right? And what exchangeable does, if you have high correlation, which we know here, it compresses that. So it's like, it's still going to have more if you have more observations, but it's going to be a lot less more the higher the correlation. So let's just go to the extreme case where we're going to say, okay, well, let's just get a new estimate that gives everybody the same weight, regardless of how many observations they have, and see, is that closer to exchangeable or is that closer to independence? All right. So what we're going to do then, I just took a subset of IDs that had at least 10 observations. So again, this isn't perfect, but that gives, I can get a regression on them alone now, right? So I can do a regression by subject now and get their particular slope of interest, and then just look at the distribution of slopes and look at the average slope and see, is that closer? If the average slope of that, where everybody just getting the same weight, is closer to exchangeable, then that's what I propose exchangeable is getting more like. It's more like mimicking a study where I had equal observations per subject. So here's all, you can look at the code I do to get this. I have to do a regression per subject, et cetera. And here is minus 50. Here's where the independence estimate was, and here's about where the exchangeable was. And you can see what it's doing when I do this, it's giving me something close to the average slope per subject. So it's like, exchangeable is more like, well, I mean, this is a perfectly legitimate estimate to get. I could just get the estimates of the slope per subject and take the average of them, and that's an estimate of the of the association. And this is what I get, something that's much closer to the actual thing I get with exchangeable. And that's it's not perfectly, because exchangeable doesn't give you equal weights per person, it just condenses the weights, relative weights. So the relative weight between people gets smaller, as less sensitive to the relative number of observations. Anyway, that's one way to do it. Now, the next, and again, perfectly legitimate estimate. And I would say this isn't exactly exchangeable. It's more close to what it's doing. So, who knows? It may be downweighting these people. I don't know what it's doing exactly. You could get more specific to try to figure out which people impact it most, what the impact, the exchangeable versus the independents. And you could probably find individuals that have the biggest impact and look at their slope, and it's probably more negative and things like that. You could do different things like that. But this just seemed a simple way to sort of get at it. It is nice that you do see like a consistently, actually it's these people, more negative. These people are positive, actually. You do see things you might expect. So we are seeing a real signal between viral load and the direction we expect. As log viral load gets higher, we expect CD4 count to go lower. Most of them are negative. And I don't know what's happening. It could be that these are based on fewer observations, so it might upweight those more relative to independence. I don't know. We could do that more detailed exercise, but it's giving you something very close to what you would get for exchangeable, which implies to me it's more like equal weights per person and not equal weights per observation. What could I do here? I should add that. I could have another histogram where I weight each observation by the number of observations to look at what that histogram looks like. Because that one should have the mean closer to 100. Let me redo, and I'll send it out to you guys. Redo histogram with weights based on number. See what that looks like. What actually, and this is just what I said. So exchangeable gives, again, it's not absolute weights that matter ever in regression. It's always the relative weights. That's the way just the math works. It's the relative difference. If everybody has weight 100, that's the same as everybody has weight 1. It's the difference between, proportional difference between the weights that changes the results. Okay. Again, I don't want anyone to get fixated on the math here, but this gives you sort of the technical explanation for what's happening. So when I'm using exchangeable, here's my estimating equation, and this is like weighted regression, except for this isn't just a vector of weights for every, you don't get a single weight for every observation, it's a matrix. So it's more complicated mathematically, but it's a matrix. It's a function of your estimated residual variance times this working correlation, right? This is what our working correlation looks like. And then it plugs in an estimate of the row hat to actually create this variable to do the weighted part. So how does the resulting weight change as I change correlation and sample size here? And then, of course, I can't look at this alone. I have to look at the inverse of it. So if you look at this thing and take the inverse of it, first of all, there should be sigma squared minus 2 hat. Here, I'll make it 1 over sigma. That's the inverse. Again, it doesn't matter what it looks like. Again, this is for somebody with a sample size of 3, so 3 observations. This is what it would look like for them. It turns out that these are always much bigger than these. So the diagonals, I'm sorry. The diagonals dominate here. So in other words, I can just look at the diagonals and how they change with rho and sigma by just summing the diagonals. Even though, again, this is not perfect because there are off diagonals. They also affect the total weight in the end, but they tend to be much smaller in magnitude when you look at them, like orders of magnitude smaller. So you can sort of ignore them. We can approximate the weight matrix as just a vector of the weights on the diagonal, which look like this. So again, if you go through all, if you go through some math and you use some approximations, you can get up with this. So the total weight of a subject, this is like just estimating an intercept only model. So again, things will change somewhat if I have covariates in there. This is, again, only to give some heuristic for what's happening. The total weight per subject will be something like their sample size over 1 plus their sample size minus 1 times rho. So you see as rho gets bigger, the total weight gets smaller for the same n, right? And the effective n will be different at different rhos. So if we just do that, here's the bottom line here. When rho is small, so this is like independence, and your sample size is 20 versus 5, your total weight will be 6.9 versus 3.6, roughly, again. Which means the ratio of weights, it's a fourfold change in sample size, gives you about a doubling of the relative weight to the regression. So it's not perfectly, it's not perfect independence, right? In independence, it would be, a ratio would be 4, be 20 over 5. But there's some correlation. If I compare now these two sample sizes, so somebody with 5 versus 20 observations, at high correlation, they're almost giving you the exact same total weight. So in other words, there's almost no difference between how they're weighting this regression in the end. Pretty much what we've been saying, but just shows you sort of approximate math. You can see it tangibly, that basically higher correlation, the more the relative weight of subjects over their observations will be diminished, the relative difference. And then at low correlation, it's more like your weight is the function of the number of observations. So that's the ticket. So again, I can have unbalanced data with almost no correlation, true correlation in there, and that independence exchangeable will be about the same estimates. It's only when you have a combination of imbalance and high correlation that you start getting these big differences in the estimates of the coefficients due to the fact that it really changes how people are weighted in the regression. All I want you to get the message is this right here. So again, if I have low correlation, imbalanced data, so some people have 5, some people have 20. The people with 20 only have 10% more weight, let's say, relative proportional weight than those with 5. So even they have 4 times the number of observations, they don't contribute that much more towards the coefficient estimates. When the correlation is low, it gets bigger. So it's more related to how many observations you have, relatively speaking. All right, so I'm going to give a review on Thursday, like a midterm review, and we'll go over this in some detail again. Not the whole time, but just to get the kind of messages for GE because they're complicated, and then try to get a sense of kind of questions on midterm. Again, I'm doing it in class, so I'm doing it not as difficult as the take-home. It's more short answer, that kind of stuff. And yeah, any questions about that or anything else today? Okay, practice these mnemonics. All right, bye everyone.